Good. All right. Hi, golfers. I'm Manish. I'm the author of Dgraph and Badger. I've given a few talks at Go Meetup in Sydney, and this is the first time for me in San Francisco. It's a huge crowd, much bigger than what we have in Sydney. You guys should send some people over. So I'm really excited. And today I'm going to talk about Badger. So what is Badger? Badger is an embedded key value database written from scratch in Go language. It is licensed under liberal Apache 2.0. Being a Go library, you can fetch it with Go get. And because there's always somebody who has this question every time we're given a talk about Badger, Badger is not a replacement for Go maps. Go maps is faster, but it is not persistent. Badger is persistent. At a very basic level, you can do these operations with Badger. You can set a key value pair. Badger accepts byte slices for both key and value. You can get that key value pair back. If we didn't do that, it would be pretty useless. And you can iterate over key value pairs with keys sorted in lexicographical order. And obviously, you can do reverse iteration as well. But before I even talk about Badger, let me explain the main motivation for building it. Quoting from a blog post by Dave Cheney, the real Australian, some people have been confronted with the problem, think, I know, I'll use CGO. Now they have two problems. We found ourselves in a similar bind when building Dgraph. Existing Go native key value databases had poor write throughput. So when we were calling RocksDB via CGO to achieve the performance, that we needed. This, however, caused us a bunch of issues. One, we were not able to use the Go CPU or memory profiler beyond the CGO barrier. Other Go tools like race detector did not work either. And the memory ownership was not clear, which caused many memory leaks. In fact, Go and CGO are at the exactly opposite spectrum of memory ownership. One does not let you free memory, the other one requires it. We also had an explicit goal that it should not be significantly slower than RocksDB. We did not want to compromise performance. So what did we gain? Not only were we able to maintain the performance, we were actually able to beat it. Using a newer design, we built a faster key value database. We also gained the ability to run Go profilers all the way down to disk and a clean Go code base through and through. We built it and have been evolving it since with less than one full-time engineer, which says a lot about the power of Go language. The launch reception had been amazing. Within 12 hours of the blog post, Badger made it to the front page of Hacker News and gained 1,250 GitHub stars in a span of 4 days. And recruiters loved it. I got 3 different emails from 3 different recruiters for same job in the same company. To give you a sense of what Badger provides, let's talk about its features. As mentioned, it is pure Go, no CGO. It is persistent, of course. While we originally did not start with it, in October last year, Badger gained ACID transactions with serializable snapshot isolation. Badger runs all read-write transactions concurrently. It does not acquire any row level or key level locks, instead using an in-memory oracle for read-write conflict detection, providing a lock-free implementation. This mechanism is roughly based on a paper called Critique of Snapshot Isolation by Mayasem Yabende. Badger does multi-version concurrency control. Each key is stored with an internal timestamp for versioning. All updates are versioned, which allows a snapshot view of the database for every transaction. Thanks to MVCC, Badger provides live snapshots of the database. We built on that to provide full and incremental backups. It supports time-based expiry for keys, and there are more features documented on our GitHub repository. So the basic design of Badger is based on Whiskey paper, which was included in File and Storage Technologies FAST, used in its conference in 2016, and claimed to be faster than both LevelDB and RocksDB. The main premise of the paper is identifying that value sizes are typically larger than key sizes. The historic need to collocate keys and values arose from the slow random read throughput provided by rotational hard disk drives. Solid-state drives, on the other hand, achieve high random read throughput, so the values can be separated from the keys, reducing the size of LSM tree considerably, which has many benefits. This basic design, along with a solid implementation, is what makes Badger faster. We ran some benchmarks over a period of time to test Badger's performance compared to GoRocksDB and BoltDB. Against GoRocksDB, Badger's write throughput becomes up to 12 times faster as value size increases. Against BoltDB, Badger's write throughput ranges from 11 times to 22 times faster on all value sizes tested. Against GoRocksDB, Badger's random read latency is 3.7 times to 5.3 times lower. And against BoltDB, Badger did not do badly, running neck to neck, sometimes performing worse, sometimes better. There are also other benchmarks which go over range iteration latencies, etc. All of these can be found on our blog. It's important that benchmarks be reproducible. All our benchmarking code is open source. We have also included a running log of our benchmark setup and execution, so anyone can follow along and reproduce them. Now that I've shown that Badger is faster, let's dig into its design to understand why is it faster. There are two popular kind of trees used to build key value databases, LSM trees and B+ trees. I'll explain them briefly. LSM trees have many levels, each level storing k times more data than the previous. Each level also has size limits. Once the size of that level is reached, a background process runs, which merges that level's data with the data in the level below it. This is called compaction. So all writes go to the top level and then get compacted to levels below it in background. The top level is entirely resident in memory. Therefore, all the writes to LSM trees are done completely in memory. This design achieves amazing write throughput with low disk activity. On the flip side, more levels need to be checked to find a key. Therefore, the random read latency is typically higher. A B+ tree is an n-array tree with each node containing a large number of children. Typically, the data is stored at the leaf nodes with the above levels acting as indices. Data gets written to the leaf nodes, and once they are full, they get split into more leaf nodes. The above index layers are updated accordingly. It's a much simpler design than LSM trees, and due to fewer levels provides better random read latency. On the flip side, this design causes a lot of random writes, resulting in lower write throughput with higher disk activity. So typically, B+ tree implementations mmap the entire database to simplify the code and potentially improve read latency. Now coming to Badger, Badger uses LSM tree-based design, but separates keys from values. This produces a much smaller LSM tree, resulting in fewer compactions and fewer levels. Badger's LSM tree size is largely proportional to the number of keys instead of the size of the values. This key value separation also results in lower read and write amplification because values never move. And the value log can be M-mapped to potentially achieve better read throughput performance. In a typical Badger setup, you can keep the entire LSM tree in RAM while serving the values out of SSD. In fact, based on a run by Usenet Express, Badger's LSM tree was only a few gigabytes, even on a database dozens of terabytes in size. Of course, your mileage may vary. Let's put this together to understand the reasons for Badger's speed. All writes are done in memory in the LSM tree, and all the value log writes are done sequentially, thus writes are faster. In terms of reads, there are fewer levels in Badger, which makes it act like a B+ tree. LSM tree being in memory means the various levels can all be checked entirely out of RAM. Once we have found the key, we can do a single random read in value log, which is served out of SSD. Therefore, even that read is really fast. To understand the design a bit better, let's see how various operations work in Badger. A write in Badger is done within a transaction. The writes get stored in a transaction local cache, and that's it. They don't touch anything else. For a read, we first check this local cache. If the key is found, we return it. And we also store the read key for conflict detection later. People who are familiar with SSI, they realize that reads are the ones that we check in conflict detection. So we store the read keys. And if it is not found, we check all the tables on various levels in the LSM tree in order, stopping when we find the key. Badger uses Bloom filters to eliminate candidate tables before searching within them. Within a table, the keys are stored in blocks of 100 keys. Each table contains a block index, which allows doing a binary search to find the relevant block easily. Within a block, the first key is the base key. The rest of the keys are diffed from this base key to save space, also known as prefix diffing. The values can be whole, or it can be pointers to the value log. So we iterate over all the keys in the block sequentially to find the right key. And finally, if it is a pointer to the value log, we can do a random read from the log file stored in SSD. We then pass the data read and extract the value. Once a user calls commit, all the reads in the local transaction cache are checked against an in-memory oracle. Oracle has a map holding the keys along with their last commit timestamp. Since the start of the transaction, if any key has changed, Oracle would flag a conflict and transaction would be aborted. If there is no conflict, Oracle hands out a commit timestamp. All the write keys append this timestamp and are batched together to form a single write request. This request gets sent to a write channel. Channel uses this technique called smart batching to batch multiple requests together and executes a single write to the value log. Note that this is a sequential disk write. Thus, the cost of disk writes is amortized against multiple commits. I sort of included the code here to show how smart batching works. Just found it to be kind of interesting. So basically what's happening is we have a request that we're reading from the right channel on the top left. Once we find something there, we'll come to a second for loop inside. We will append it to a request slice. And then we finally go to the select channel there, where we keep on greedily looking for more requests from the right channel. If we find some more requests there in that for loop, in the internal for loop, we'll keep on increasing the slice of the requests. And finally, when the right channel is completely empty, we'll push something to the pending channel and jump over to the right case where we will actually do the write. We went through a bunch of iterations to get this loop correct. So I found it to be an interesting piece of code to share. And the pending channel actually just means that we can only do one pending write to value log at a time because files can be written sequentially only. So coming back to the commit, once we have value pointers from the value log, the key plus value pointer is written to the LSM tree. If you do some rough calculations, if the diff key size is 16 bytes with 10 bytes for the value pointer, then a 64 megabyte table can store 2.5 million keys in a single table. That's pretty efficient. And that shows how Badger produces smaller LSM trees. So writes to LSM trees are done in memory, as I mentioned before. In case of a crash, it can cause these mem tables to be lost. Badger uses value log as a write-ahead log to recover from crashes. All the updates go to value log first. Once persisted to disk, they are applied to the LSM tree. On restart, Badger replays values from the value log from the last safely persisted state. This regenerates the lost tables from the LSM tree, bringing Badger back to its correct state. And Badger has a way to identify transaction boundaries. So it ensures that it picks or drops a transaction as a whole. Now that's a fair idea of how Badger's design works. Let's consider some complexities associated with this design. First is the quirky behavior of file systems. A lot can be said about this, but let's look at a few quirks. To make this interesting, I'm going to pose some questions. So with a raise of hands, people who think yes, raise hands, who think no, keep their hands down. Would a file delete reclaim space in the file system? Who thinks it would happen? Who thinks it would not happen? Would closing a file sync its contents to disk? And who thinks it would not happen? Few people. People need to participate more. Can a new synced file, a new and synced file be lost? It can be lost. And who thinks it cannot be lost? More people think it cannot be lost. Okay. All right. Let's jump to this. A file delete does not necessarily reclaim space as observed by the file system. We found it the hard way. So adding a file truncate operation before deletion really helps. Closing a file does not sync its contents to disk. So explicitly sync a file before closing it. A newly created file, despite being synced to disk, can be lost. Sync the directory if you add or delete files. A directory is just like a file. It can be opened and synced just like a file. Also, a crash can result in garbage data returned to the end of a file. So add checksums to know which log entries are still valid and truncate the file once they are not. So we have some more issues that we found over time, including doing live garbage collection for value log. I won't go into that because we are slightly short of time here. So who should use Badger? Let's first address who should not use Badger. Don't use Badger if you have a single-threaded sequential workload, because the cost of Go channels and disk writes in Badger does not amortize well. It was not designed for that purpose. And Badger might not be a good fit if your entire database can fit in RAM and write throughput is not important to you. Use Badger if you want to achieve a performant read-write workload and want to avoid CGO. It works really well when called concurrently. That is, many Go routines are reading, writing data simultaneously. Badger is a great choice if you need access to versions. Badger can store multiple valid versions for the same key. It comes with a mode which gives you direct access to the version dimension. This simplifies a lot of transactional nuisance associated with building an MVCC layer above Badger, like we've done at Dgraph. In a short period of time, Badger has gained quite some following. It has over 3,100 GitHub stars with 36 contributors, currently at version 1.3.0, which means it's stable for production usage. And it's used by various projects, including GoIPFS, Zero Store, and Usenet Express. And if you are using Badger, do let us know so we can add your name in the repository. Research is moving ahead, and there's a newer paper which further improves the performance of LSM trees by optimizing compactions, which seems very interesting. Implementing such papers is something that we will want to continue trying. So check out the Badger repository and use it in your next project. And if you want to help improve Badger and Dgraph, know that we are hiring, so come join us. Thanks. Questions?
All right, so the deal is if you ask a question, you have to wait for me to get to you. Oh, wait. Oh. So we're recording, but you should also know before you ask questions that we're recording because I'm supposed to disclose that to you. So that's why you have to say it into the mic.
I missed the intro. What does Dgraph actually do?
I never intro Dgraph. I was told I'm not supposed to promote commercial products here. Dgraph is a distributed graph database. Yeah.
Thank you for listening, too. Okay. All right. I'll come back to you. I see you back there, and then that's all, because you were so prompt and you raised your hand quickly.
I don't know if I missed it. There was a lot of code flying by, but if you delete, do you get disk fragmentation, like basically like empty stuff, and is there a compaction or something that you have to do occasionally for that?
If you delete files, you mean? Keys. So if you delete keys, essentially what you're doing is you're marking the key as delete. You're not really it doesn't get removed immediately. And at some point, when the value log garbage collection runs, it would go over the key value pairs which are inside the log and figure out if they're still relevant, if they're still expired, if they're expired or deleted. Then it would punch a hole in the file to reclaim that space. And eventually, when the entire file has been punched, it would delete that file and reclaim that space completely.
Yes, my question about Dgraph language. Do you have any plan to produce Dgraph Lite in a manner serverless Dgraph, like SQLite?
SQLite?
No, not SQLite, Dgraph Lite. Like SQLite for SQL, Dgraph Lite for Dgraph.
You mean embedded Dgraph?
Yeah.
We actually did have embedded Dgraph before, and we realized that it was just not being used as much as the normal Dgraph. And we also broke away some part of the functionality into a separate binary, which is the Dgraph 0, which is the coordinator for the cluster. So it just was making it harder for us to try to maintain this embedded version, and we just removed that piece of code. So it's no longer embedded.
All right. Thank you so much.
Thank you.